I wrote an abstract that caused this work to happen, and so they give me credit. I'm like the third one down. But the guys who actually did the work, I can't pronounce their names, but there they are. And they're really great. And the really neat thing about writing an abstract and having some grad students think about and try to write some code around what the idea is that they think of things that you wouldn't necessarily have thought of. And some of them are kind of interesting, so I'm pretty excited about that. This work came from some work we did at ARIN. I'm on the advisory council of ARIN, so when the public policy meetings happen and there's consensus in the community, we try to help formalize policy changes and make sure that it represents the consensus of the community. So when we started changing things like from a /19 minimum allocation to a /20, we started thinking, well, gee, what happens to the global routing table? Is there some way to look at it? And so I went around for a lot of time because I have limited programming skills and limited amounts of time and said to people, gee, wouldn't it be great if we knew X, or wouldn't it be great if? And so people like Philip Smith, who does the weekly routing table report thing, has breakdowns by regional registry now. And some of those things answered some of my questions, but my main questions were things like, how do actual allocations affect the routing table? So when a registry hands out a block of address space, how does that affect the table? And so this is more focused on the routing table while looking at address allocations and assignments, as opposed to, how much could we aggregate the routing table based on, AS path lengths or whatever that everybody else talks about. So it has more of a registry focus. And I don't have any idea what my first slide is. Oh, okay. So a little overview. I think you guys are all familiar with most of this stuff. The Internet Registry to assign address blocks. And I want to take a minute to explain the difference between assign and allocate. In this talk, we use them interchangeably, but there really is a distinction. When an address registry assigns a block, it's to an end user, and it's not a block to be subdivided and handed out to customers. If it's allocated to an ISP, and then it's sub-assigned to customers. In this talk, we use them interchangeably, but they're always assignments and allocations from a registry, so they're not sub-allocations that an ISP would do to its customers. And we look at also a little bit at the routing table evolution, but again with an allocation and assignment slant. And some conclusions, and I came up with some more in my sleep last night. So again, this is what I just talked about. Some of the policy changes, again, are the change to CIDR, and I have some slides on that are no big surprise. And the change from a 19 to a 20, which we really wanted to see if it had any effect at all. So how have the address assignments been performed? What are the block sizes over time, those sorts of things? What are the distribution of prefix length? And again, these are of allocations and assignments. So let's look at some of these charts. So in 1993, before we had, CIDR was deployed, it's no big surprise that the allocations were 16s or 24s, because that's all we had. We had the 3 bears, the /8 was too big, and the /24 was too small, and the /16 was just right. Only it wasn't, it was huge. So, and then after CIDR, a lot of different size prefixes started being assigned, so there's no big surprise there. Again, when we changed from a 19 to a 20, again, there's no really huge surprise. It used to be that there were a lot of 20s allocated. Now there are 19s. Now there are a lot of 20s. So no big surprise there. Now, if you look at allocated blocks over time, these were I was thinking about removing these from the slides because they're a little bit deceptive, but nonetheless they're a little bit interesting at the same time. So if we look at the different years, you see the allocation of blocks over time, just how many. And the yellow is what the grad students called non-aligned blocks, which is the part that's a little bit deceptive. One of the registries does assignment and allocation in the database slightly different than the others. So if a block gets assigned, say a company can only justify like a 19 and a 20, but not a whole 18, in the database it'll show up as one contiguous non-bit aligned block, even though it's really 2-bit aligned blocks and it's assigned as 2-bit aligned blocks. And then there's usually a reserve space for the rest of the 18, and then if they go back in the right amount of time, they fill up that space, and then they have one 18. So it's a way of trying to promote aggregation, not aggravation. But in the database, they didn't know that because they're not, they don't go to registry meetings. They don't get address space from the registry, so it wasn't something that they thought of. There are, however, a few really interesting non-aligned blocks, and I have an example later on. Also notice that there are blocks that are assigned that are longer than the minimum allocation, and most of these are because of the micro-allocation policies. And again, the scale's a little bit different, so there aren't really a huge number of these non-aligned ones. So this is an example. There's a couple examples, and this has nothing to do with this address block. Like, it's not their fault. I don't know whose fault it is, but anyway, it's not a bit-aligned block, and actually it's broken into a bunch of smaller bit-aligned blocks, and if you look in the database, that's how it's represented. There's another one we found. I was talking to Richard last night from Aaron, and he knows all these intimately, so we're going to work with him to help identify what some of them are just assigned a long time ago. But there's a /16 where they have the whole /16 except for the last /24, which makes for a really nice non-aggregatable block. And again, like I said, some of them are not bit aligned just because of the way they show up in the database, but they really are. And so we're going to tease those out and include them appropriately in the data sets. But it's just so small that it didn't really affect the analysis anyway. So how do these allocated and assigned blocks appear in the routing table? Do they appear as they're allocated? Are they aggregated? Are they fragmented? I'm going to talk about that some more. How long after they're allocated do they show up in the routing table? Are there some that don't appear at all? We all know there are, but we've quantified that. We used the RIPE data, we used the route views data, and compared some of that to the links data. And as you know, there's nowhere that you can look on the internet and get a full picture of what the routing table looks like from every vantage point, but we feel like we've got a pretty good handle on it. The total prefixes allocated in our study period were 9,554. So do all the prefixes appear? This is a month-by-month graph of the number of allocations, and the green are the ones that have never been advertised. So as you can see, over time, there are certainly blocks that don't get advertised. And it seems like in 2002, there are a lot of them compared to the number that are allocated. This is one of the interesting things that I don't know if I would have thought of looking at necessarily, but they did, and I think it's kind of cool. So they looked at the difference between the amount of time between when a block gets allocated and it shows up in the database and when it shows up in the routing table. And as you can see, there's 108 allocations that have a delay that are greater than 400. So there's, for any time frame that they pick, there's still a lot of outliers. But the really interesting thing that I think is interesting is this graph, this chart. I removed the blocks because, well, I kind of was told I probably should. So, because I didn't want this to be an expose or whatever. But there are a bunch of blocks and their allocation date. And notice that there are some from each of the regional registries. LACNIC was too new to really tell. But this actually shows that there's a negative delay. So it's showing up in the routing table significant amounts of time before it shows up in the database as being assigned. So we're trying to figure out, and I talked to Richard quite a bit last night about what some of these could be. He said that some of them might be transfers, that in Aaron's case, when they transfer from one organization to another, it shows up in the database as a new allocation with a new start allocation date. So some of these might be that. Some of them look like they were assignments back before there was Aaron or RIPE or APNIC. So maybe they weren't actually in a database, but they needed to change their inaddr or something, and then they ended up showing up in the database. So we're in the process of looking at them. But it's pretty significant. 1,500 days that a prefix gets advertised before it gets assigned by the registry. That's pretty big. So how exactly do the allocations show up in the routing table? Do they show up just as they're allocated? Are they fragmented? Are they aggregated? I have some examples, and then the last four are combinations. So if it in the graphs, if it shows up as identical, then the only advertisement for that block is identical to the allocation length, and then there are combinations at the bottom. And this is an example. I don't really think I need to go through it, but if it's a 16, then it's advertised as a 16. And if it's fragmented, then the 16 isn't there, but some of the fragments are. So anyway. So if we look at some of these graphs, this is for all of the allocated prefixes in our study period. And some interesting things to take note are that 48% are advertised as identical to how they're allocated. But there's a whole bunch that aren't. So another 40% are some variation of fragmented, which means a lot of things. But to me, if you're looking at changing the policy, it might mean that maybe you don't want to start assigning little assignments to each person who comes, because for 40% of the prefixes, an ISP who's trying to save their routers from keeling over could filter out those more specifics and trim down the routing table and still be able to get to those prefixes. I mean, there's lots of other things you could say about that, but that's the thing that strikes me today. So if we look at these more individually, for /16s, they change a little bit more over time than just the whole picture. They have a higher fragmentation rate than any other size block we looked at. They also seem to get replaced, instead of just being identical, they get replaced mostly with identical plus a fragment. So somebody's injecting a hole for one reason or another out of these 16. So that's why the identical line, the blue line, is going down, while the little, I don't know how well these are to see, the little turquoise bubbly things are going up. It might be good, actually, if you pull up these slides on the web if you're interested in looking at them, because some of them later on are a little bit more difficult. So 19s, I actually didn't find this overly surprising. They tend to be advertised as 19s, and I think that's because of the filtering policies that we had for so long, and some of the people that wholeheartedly enforced those policies. 19s seem to be, really highly identical to how they're advertised. Let's see. 20s are also interesting because 20s tend mostly to be aggregated into 19s. So if you get allocated 20s from the registry, over time you're more likely to aggregate them, and you're more likely to aggregate them into 19s. And again, I think this is an artifact of the policies, the filtering policies that were beaten into our heads for so long. Okay, this graph shows the average number of prefixes, of fragments of allocated prefixes, which kind of hovers around 14. The little blips that are way up near the top, around month 30, are because of a deaggregation event of net 63/10. And the rest of them, so over time, it grows a little bit, but it averages around 14. So one of the things that I wanted to know was, everybody talks about how /24s are a big component of the routing table, and I kind of wanted to figure out, are those allocated as /24s? So how many /24s in the routing table are actually allocated as /24s, and how many of them are deaggregations? And we could have done this for any length prefix, but since /24s are the largest component right now, we decided we'd look at those first. So of the length of the allocated blocks is the x-axis, and the little towers are how many are advertised in an aggregate. So like out of 1,008 /18s, 142 are advertised as part of an aggregate. So this kind of gives you an idea of the amount of aggregation that's going on. Let's see. This shows that 10% of the allocated blocks contribute to 70% of the routing prefixes, and 90% of the allocated blocks contribute less than 30% of the routing table prefixes. So, I think that the stuff that was talked about earlier of going out and trying to get people to aggregate, it's a pretty small target, and probably could do a lot of good if you can get to those 10%. So here's some more on the /24s. So before 1993, a lot of /24s were allocated. No big surprise. It was that model where someday we'll be able to aggregate them. So let's give somebody, 30 of them instead of a /16. So and over time, fewer and fewer of them are allocated. So this is just the number allocated per year. And then if we look at /24s as fragments of larger allocations, so year by year, you can see that a lot of these are fragments of larger allocations, especially like in 99 and 94. But some of the early ones I think are probably because people just never aggregated them after they could aggregate them. And this is a breakdown of /24's fragments per the size of the block that they're deaggregated from. So like for a /16, there are 14,307 /24 fragments out of 1,406 /16s. Let's see. So 58,329 are fragmented from larger allocation blocks. And most of them came from /8s through /23s. Let's see. So if we look at this per country, I guess they decided that maybe it would be cool to see if somebody is worse than somebody else country-wise at aggregating or deaggregating. And you can see that they're pretty much the same. So the U.S. is about 6.8%. So the average number of routing entries that are fragmented from an allocation block are 6.8 in the U.S., 6.7 in China, 6.2 in Japan. So they're pretty much the same. It seems like Canada does a really good job of aggregation. Yay, go team. So let's see, changes in the global routing table. So let's look at how the allocations, some more about how they show up in the routing table. How many prefixes get added? How many prefixes go away? Where do they go? Things like that. And also, when we talk about IP addresses being consumed, it's basically they aren't necessarily reachable, but they're represented by the routes in the routing table. So if a /24 is in the routing table, then that address space represented by that /24 is consumed, even if 3 of the addresses or whatever, all of them aren't reachable, the route's there. So this is a standard graph of the growth of the routing table size. And if you look on the graph on the right, the dashed line is the amount of allocated address space, and the blue line, I hope you guys have colors, the blue line is the amount of address space that's actually represented by the routes in the routing table. So it's consumed, as we call it in the paper. So the routing table size in our study period changed from 53,000 some routes to 114,000 routes, and depending on your view of the world, that can change. So the growth has been really huge, and again, the growth in address space consumption, so the amount of address space represented by the routes in the routing table, has only grown 26.3%. And let's see, that's pretty good. So where did the new advertisements in the routing table come from? The total number in our study period was 87,941. And we wanted to look at the relationship between those and allocations. So 88.4% of them are fragments of larger allocations. 10% of them are allocations of equal size. And a little smaller ones are aggregations of multiple smaller allocations. So let's look at this. So this is where the new advertisements come from as far as the year. So these are allocated blocks in these years and which ones, how many showed up in the routing table, and then by country. So the U.S. had the most, and the other ones were smaller. So I guess it's no surprise we have more deaggregation. I guess we have more prefixes. So if we look at the pie chart, what does the pie chart say? The fragmented ones, so when advertisements leave the routing table, some of them get discarded, so they're just not represented by anything. Some of them get aggregated. A lot of them get aggregated, like 77% of them get aggregated into other prefixes. So one prefix may go away, but it gets replaced by another one. And then some of them get further fragmented. So the prefix itself went away, but then there are more fragments sitting there. Let's see. This is going faster than I thought. Okay, so this is a breakdown of the newly announced prefixes by length, prefix length. And there are, like we said before, there are a lot of /24s, but there are a lot of other ones too. And if they're all fragments of larger allocated blocks, then a lot of these little guys get filtered out and you are still reachable. Of the ones that went away, so there's 30,000 that went away and 80,000 that showed up. 22,000 of them were /24, so they're still, they go away and they come, you know, there are new ones and then there are ones that go away. And the impact on address consumption. So when prefixes go away, there's still the discarded prefix. Let's see here, sorry. So the total number of addresses covered by the prefixes was 2,400,000, and the total number of addresses that drop off was only 131,000. So there's a bunch of them that become unreachable, but there are a lot of them that just get re-represented by other prefixes. So what are our observations? It's no big surprise. Allocations play a dominant role in the routing table size because, you know, you have to advertise your address space to get it reachable. So when we hand out blocks, it's no big surprise that the routing table is going to grow on some level. Hopefully people aggregate better than they, you know, they do it well. The 19 to 20 change, it had an impact, but I'm not really sure that it had an impact that would be any different than if we'd stayed at a 19. Now that's not to say that we should go, I still don't believe that we should go and give everybody a portable prefix that isn't part of a provider block, even if they punch a hole in that provider block, because it takes away your ability as an ISP to filter it out, but that's my opinion. Also, remember that there's no requirement that an allocation get advertised in a particular way. So, you know, if you go and you get a block from an RIR, there's no requirement that you advertise it aggregated or fragmented, and maybe some guidelines would be good, but I don't think that that's the role of the registries to do that. So what we would like to know is whether this is interesting, what other things you think would be useful. If you have questions or comments, that would be great. Nobody? Oh, okay. We really want feedback, so.
Hi, it's a nice talk. It's Andy August from Renesas. I think that the prefix churn is actually much larger than you see. I mean, we have seen from about, what, few dozen peers that we have something like 350,000 distinct legal prefixes this year. Many of them appear for a short time or appear only for certain peers, for certain peering crowds. So people rearrange and keep rearranging prefixes or leak prefixes at a much higher rate than the semi-static picture of the routing table growth shows. So that's just a comment.
Oh, okay. Where are you? Like, is there a way that we could connect to something near you and look at that?
Yeah, we can talk offline now.
Okay,
after
great.
the talk, yeah.
Because it all depends on your view of the world.
Yeah,
So,
we are peering with routers in South Africa, Asia, Europe, and the United States.
oh, great. It's Avi. Oh.
I'll just say that we see the same thing, but in many cases it depends on looking at ISPs that you might not think of, that don't peer, that you don't find you know, at major exchange points, but that do some peering, especially some peering amongst themselves, you know, and internationally where people who do peer, you don't have their BGP sessions logged. So I'd say that, you know, looking at edge and looking international, and I don't know exactly what the number is, but it's in the hundreds of thousands of distinct things that we've seen pop up for some period of time, looking at BGP from Akamai.
Okay. Anybody else? Thanks.